again, and welcome back to Chapter 2. Chapter 2 is dealing with atomic and molecular structure of matter, and in this video we're going to take a look at exercises 3 through 6. These exercises deal with the crystal lattices of solid structures, and in exercise 3 it's talking about the crystal structure of the metal indium. In exercise 4, the crystal structure of diamond. 5, sodium chloride's crystal structure, and 6, cesium chloride's crystal structure. The last of the exercises, 7 through 10, we'll deal with in our third and final video for this chapter. So let's have a closer look at exercise 3. Hershey is back on her ledge. She likes hanging out next to that owl, and maybe it's the pineapple, maybe it's the owl, I'm not sure. We have another cat who's terrified of that owl, and so I had to put it outside, but Hershey can't see too well, so I guess she doesn't mind the owl. Got another cat over here looking at me through the doorway, wishing it could go outside. Sorry, Silver. Maybe some other time. So we have the problems right here for you. Now I should warn you, a lot of files open on my computer, so I might get a little bit confused in trying to show you things when dealing with these questions. Question 3 is kind of involved, and I'd like to take a really good look at this material. Okay, so I want to show you a lot of things. It'll take us a while to go through question 3. So let's take a look. The question says, the metal indium forms tetragonal crystals. We'll talk about that in a second. The unit structure is a rectangular parallelepiped with edges A is 3.24 angstroms, B 3.24, and C 4.94. There are 2 atoms in the unit structure with coordinates 0, 0, 0, and 1/2, 1/2, 1/2. And this problem is in 3 parts. So we'll take a look at these 3 parts in a moment. First, I would like to show you what a tetragonal crystal looks like, and what these coordinates mean, and so on. So let's take a look at my paper. So here, let's put that up there, and I'll bring this down here. So crystal structures and lattices are discussed on pages 20 through 26. That's where you'll find most of it in Chapter 2. Although there is a couple of appendices that deal with crystallography as well. You might want to take a look at. They're pretty involved. Now, a tetragonal crystal is a rectangular parallelepiped, which means that it's all right angles. All of these faces are right angles to one another. Okay? But it's not a cube. It has 2 of the edge lengths are the same. So A and B are the same, but C is different. And in this case, C is a little bit longer, 4.94 angstroms. Now, this crystal structure of indium has atoms at 0, 0, 0, and 1/2, 1/2, 1/2. These coordinates are relative coordinates corresponding to the edge lengths. So it's it's 0 in the A direction, 0 in the B direction, and it's 1/2 of it's 0 in the C direction. But this one is 1/2, 1/2, 1/2, which means 1/2 in the A direction, 1/2 in the B direction, and 1/2 in the C direction. Okay, so relative coordinates. Now, one thing that might not be immediately obvious for crystals and crystal structures is that all of the atoms in the crystal structure have similar environments. You don't really see that by looking at just one unit cell. All I see is one unit cell and two atoms. So I'd like to show you what the entire crystal lattice would look like, what lots of unit cells stacked together actually looks like. And I have for that a simulation software package. So I'll show you that. So this is where I might get a little flustered. I have a lot of stuff floating around on my computer right here. So I'm going to follow my notes pretty closely. So this program is called VMD, Visual Molecular Dynamics, and it's an awesome open source software package for simulating molecules and for rotating them around in space and seeing what they look like in all perspectives. So let's draw one unit cell. So there is our tetragonal unit cell. And let's go ahead and put the atoms in there. Okay, so there's the atom at 0, 0, 0, and there it is at 1/2, 1/2, 1/2. Okay, but this is just one unit cell. An entire crystal lattice basically stacks these boxes in all directions to fill up space. And so let's stack some more together. So here's two unit cells stacked back to back and along with their atoms. All right. Now the way it's drawn right here, the atoms aren't touching each other, but in reality the atoms do contact each other. Okay, so we'll take a closer look there, but when we draw the atoms to scale, it's kind of hard to see everything. So in a moment, we'll draw them to scale. But let's stack a few more unit cells together. So here's a 2 by 1 by 2. So 2 unit cells in the x direction, 1 in the y direction, and 2 in the z direction. All right. And we can do more than that. 2 by 2 by 2. Okay, along with their corresponding atoms. And how about a bunch of them? So let's 10 by 10 by 10. Okay, so quite a large lattice, and this is tiny in the you know, in an actual crystal. You got trillions and trillions and trillions of unit cells. Okay, so maybe you're beginning to see that all atoms have similar positions, but it might be a little bit easier to see if we draw the atoms to scale now. Okay, so the atoms in reality do contact each other, and what this 10 by 10 by 10 lattice shows us is that it's basically one layer of particles staggered with another layer staggered. The layers are alternating, and there's nothing really different between this layer and that layer, right? The atoms are all in similar positions, and it looks the same if you were to look at it from this direction, right? The atoms are just all packed together. So you see, maybe you can see it better like this. You have one layer, and then the next layer is staggered, and then the third layer is right on top of the first one, and then staggered again. All right. So there is the crystal structure of a tetragonal crystal with atom positions at 0, 0, 0, and 1/2, 1/2, 1/2 for each unit cell. All right, and hopefully you can see that all of the atoms look very similar. They have the same sort of environments. Let's go ahead and remove that lattice. So now it's just the atoms, and the lattice is really a mental construction. The cells and everything. So you can't distinguish like one layer from another one. Okay. So with that being said, let's go ahead and read our problem again. Here's our problem. So part A asks to calculate distances from each atom to its 12 nearest neighbors. Note that 4 are at one distance and 8 at another distance. Okay, so take an atom. It has 12 nearest neighbors. What are the distances to those 12 atoms? 4 should be one distance and 8 should be another distance. So let's get a better look at the 12 nearest neighbors. So put this back there. So I'll show you this in a second. Okay, and for that, let's do a 3 by 3 by 3. Okay. Now, this is 27 unit cells, 3 in all directions. And all of these atoms have similar environments. So let's go ahead and focus on the exact middle unit cell. So 2 in this direction, 2 in that direction, and 2 in the other direction. So the central unit cell. And we're going to focus on the atom that's at the 1/2, 1/2, 1/2 position. And so focus on these atoms. I'm going to just color them a little bit differently. So keep your eyes fixed. Okay, you see they didn't change right there. So we just colored the central atom black. So here, let's get rid of the rest of it. So we have the central atom is colored black, and you see this atom has 4 other atoms that are at the 1/2, 1/2, 1/2 position in the neighboring unit cells, and they are all the same distance from this one. Okay, but then there are 8 atoms that are in similar positions relative to the central atom as well. So we should be calculating 2 different distances. Now, I'm going to leave this right here, and I want to show you a drawn representation of this. So here, let's leave that right there, and let me show you a drawing that I did. Okay. So you see, this is the same as what we're looking at on the model. So there's the model. We have our central atom, and then 8 atoms at the corners of the unit cell, and then these 4 other ones through the faces in neighboring unit cells. Okay, so there it is, and there's my drawing. So here's the central atom. We're going to label that X, and you have the 8 atoms at the corners. These are A1, A2, A3, A4, A5, A6, A7, A8. Okay, and then you have these 4 other atoms, B1, which is out here, like out of the paper in this direction, B2, B3, and B4. Okay, now the problem wants us to calculate the distances between these atoms and the central atom, and so we really need to calculate 2 distances. All right, so 4 atoms are going to be at 1 distance. These are the atoms B1, B2, B3, and B4. Okay, those are all the same distance from X, and it should be clear to you that this distance equals the edge length. which is 3.24. After all, if you're looking at your central atom right here, to go up to this one, well, you have to go up to the face, which is 1/2 of the edge length, and then back up to all the way up to this atom, which is another half. So this distance is going to be the entire edge length. It's going to be the same as that edge length, which the problem says is 3.24. Okay, so we got one. Now, the other 8 atoms, 8 atoms are at another distance. These are atoms A1, A2, A3, those right there. They're all at another distance. Now, to calculate what the distance is between A1 and AX, or A1 and X, what we're going to do is we're going to consider a right triangle. Okay, if you look at these 3 points, this one, and this one, A1, A4, and A7, that is a right triangle. This is the right angle right here. Okay, A1, A4, A7. So I went ahead and I have drawn that triangle right here, a representation of it, A1, A4, A7. Now the distance between A1 and A4 is known. It's 4.94 angstroms. That's the length of the edge in the z direction. Okay? And you should be able to easily figure out that this is going to be 3.24 times the square root of 2. Right? The distance between A4 and A7, the distance between these two, if this edge is 3.24 and that edge is 3.24, and this is going to be 3.24 times square root of 2. Okay? And the length of the hypotenuse we'll just call h. Okay? Now we can use the Pythagorean theorem to solve for h. It's going to equal square root of 4.94 squared plus all of that squared. And when you calculate h, it comes out to 6.37 or 6.7379. And the distance between x and atom A1 is going to be 1/2 of the hypotenuse. So that comes out to 3.37 angstroms. All right? So 3.37 angstroms is the other distance. You got 3.24 and 3.37. Now, just to demonstrate that, the simulation package that we're using can calculate distances really easily. So let's go ahead and get the distance between these two and the distance between those two. And there you go. We got 3.24 and 3.37. All right. Okay, looking at part B, it says, show that if the axial ratio C over A were equal to 1.414, that's the square root of 2, the 12 distances would be equal. Okay, so that's a little bit different ratio than what's in part A. In part A, 4.94 over 3.24 is a little bit bigger than the square root of 2. Okay, if we calculate that, 4.94 over 3.24, well then that's 1.524. So in part A, the ratio of C over A is 1.5246, but in part B it says, well, what if the ratio were equal to the square root of 2? Show that the 12 distances would be equal. So what this is talking about is, on our diagram here, these 12 distances, in part A, the 8 distances for these atoms were different than the 4 distances for those atoms. Okay, this was 3.37, and that is 3.24. But in part B, all of the distances should be the same if this ratio C divided by A equals the square root of 2. Now this is very easy to calculate. So if C over A is square root of 2, then C is A times the square root of 2, okay, which is 3.24 times the square root of 2. And in that calculation for the hypotenuse in the last problem, instead of 4.94 squared, it would be this quantity squared. And so when you calculate the hypotenuse, it simplifies to twice 3.24, or 2 times 3.24. And so the distance from x to a1, which is 1/2 of the hypotenuse, this time it is 3.24 angstroms. Okay, so this distance is also the same as the other distance. Now I'd like to show you another thing with the simulation, how part A is a little bit different than part B. Okay, so let's show that to you. Here's part A. You can see the two distances are different. Okay, and let's just go ahead and redraw the 3 by 3 by 3 lattice. Okay, and we'll put that up here. Okay, let me put that up there. Oh, get me off of there. So there's that. Now you see how the atoms are not contacting each other. Okay, right here. Here is the central atom X, and here is atom A1. They're not contacting each other. Okay, but these atoms, in fact, are contacting each other. So that shows you that the distances are different. This is 3.24 angstroms. That's 3.37 angstroms. Now down here, I'd like to show you the lattice for part B. And all the atom distances are the same down here, and you can see that looking at pretty much the same angle, the atoms are in fact contacting each other right there. So they're touching each other here, and they're also touching each other there. That's because these distances are the same as those distances. Other than that, you know, if you were to zoom out, it might be kind of hard to tell that they're, you know, actually different lattices. So slightly different lattices. Here all the distances are the same in part B, and here two different distances. Okay, now in part C, it asks what is the relation between the unit of structure with this axial ratio. So in other words, what's the relation between the lattice for part B and the cubic unit of structure that's described in the text for cubic closest packing? Okay, so part C is asking what's the relation between B's lattice and the face-centered cubic lattice. That's the cubic closest packing, face-centered cubic. Okay, what's the relation? And well, the answer is that they are the same. They're one and the same. So to show you this, I want to put these two lattices right next to each other. Let's take a look at what the face-centered lattice looks like. And let me get the images prepared. All right. So here we go. You can see the lattice for part B. All right. Now let's go ahead and draw a 10 by 10 by 10. right, and let's put that over here. And then for the face-centered, what this is it's a unit cell that has 4 atoms associated with it. Okay, one is at 0, 0, 0, and then another is at 1/2, 1/2, 0, and then you have this one is at 1/2, 0, 1/2, and then this one is at 0, 1/2, 1/2. Okay, if you look at the coordinates for the face-centered lattice, those are the coordinates of the 4 atoms associated with that unit cell. And we could draw lots of unit cells. Let's go ahead and do that. Let's make a 10 by 10 by 10 lattice along with the atoms. Okay, and there it is. All right, now perhaps you can see, you know, the more common face-centered lattice that a lot of Gen Chem texts show you. They have an atom at each corner and one at each of the 6 faces. Okay, so that's the face-centered lattice right there, and that is also the same as this tetragonal lattice. Now it's kind of hard to see. It looks like they're different. Looks like, you know, when you look at it at this angle, these 4 atoms looks like a rectangle, whereas if you rotate this one, it's a square. This is obviously different than that one. Well, no, they're really the same. Okay, and I'm gonna demonstrate that to you in a second. But one more thing, there is another way to draw the face-centered lattice. Let's put that down here. Sometimes you'll see the face-centered lattice drawn as closest packed layers. Okay, so down here, this is another way to generate the cubic closest packed lattice, and textbooks will commonly show you this. So here's one layer where the atoms are packed very tightly together. They cannot be any more tightly packed together than that. And the second layer is stacked right on top of the first one with the atoms in the crevices right there. So you see the atoms in the second layer are stacked right on top of the first layer in the crevices. And then the third layer gets put into the crevices right here on top of the holes between the first and the second layer. Okay, and there you go. And you can keep on stacking layers in a closest packed fashion. Okay, and you can keep on doing this. The fourth layer is actually directly right over the first layer, and the fifth layer is directly over the second layer, and then the sixth layer is directly over the third layer. And you can keep on going up. You know, you can get a 10 layers thick if you want. Okay, there you go. Now, I'm going to demonstrate to you that all 3 of these are the same. So this is the tetragonal lattice in part B up here. This one over here is the face-centered cubic lattice that the textbook talks about. And here is a stacking of closest packed layers that you'll also sometimes see representing the cubic closest packed crystal. Okay, and the way we demonstrate that these are the same is we color code the atoms. So let's look at this one. We're going to color code that. Okay, you see this one actually consists of layers of red, yellow, green, red, yellow, green, red, yellow, green. Okay, and let's rotate that around like this. Okay, now let's do the same thing for this. Let's color code this. There we go here. And this one also has layers stacked: red, yellow, green, red, yellow, green, red, yellow, green. Okay, and so does this one. Let's color code that. There we go. And let me make sure I rotate it the right way. So there we go. So red, yellow, green, red, yellow, green, red, yellow, green. All right. Now the way we demonstrate that these are in fact the same is we can make this lattice look just like the face-centered cubic lattice, okay, by cutting away atoms. So this is problem 3 part B's lattice, the tetragonal lattice. You can see those tetragonal unit cells. So let's cut away atoms and we're going to expose the face-centered lattice within there. Okay, make sure I'm cutting away the right one here. Where's that? There it is. Okay. You see? If you just remove atoms, I'm not changing the actual structure, I'm just removing some atoms. And you can see that we're exposing within this tetragonal lattice that same face-centered cubic lattice. Okay? And here, you know, you can see the 1, 2, 3, 4, 1, 2, 3, 4 is the same as right here. 1, 2, 3, 4, 1, 2, 3, 4. Okay? So they're the same. And we can do the same thing with the closest packed structure down there. So let's expose within this layering system the face-centered lattice as well, and you'll see that they're all the same. You see? They're the same. All right, so it's really 3 different ways to represent the same packing of particles. All right, so I hope that helps you see this. Let's check out problem 4. Diamond has a cubic unit structure with edge length A equals 3.56 angstroms. All of the edge lengths are equal to this since it's cubic. There are 8 atoms in the unit with coordinates, and it gives you the coordinates of all 8 atoms. How many nearest neighbors does each atom have? What is the distance to each of these neighbors? So the textbook gives us the answer. There are 4 nearest atoms, and that's the distance. So let's check out this unit cell. I've drawn it here for you. Now, problem 4 also references the same page numbers in the textbook. 20 to 26 discusses crystal structures. And here is the unit cell with all 8 atoms drawn to those coordinates. So the edge length is 3.56 in all directions. And there are 8 atoms per unit cell. Now, the atoms have been divided into 2 groups, A1, A2, A3, and A4, and those are using the first 4 coordinates, and then B1, B2, B3, and B4 using the second set of 4 coordinates. And I went ahead and rewrote those coordinates right down here for you. All right, so the A's are color-coded pink and the B's are color-coded green. Now, the reason for that is because each of these atoms, B, for instance, B1, is surrounded by 4 of the atoms of A. And each of the pink atoms are likewise surrounded by 4 green atoms. Okay, but again, it's kind of hard to see this with just one unit cell, and I'd like to show you the computer model again, which draws lots of unit cells. So let's take a look at that. So here's VMD again, and here is one unit cell, a cubic unit cell. Let's move this down there and see if we can give it a slight rotation. Some VMD will let you rotate things slightly. Okay, there we go. And let's put the atoms in. So these atoms are carbon atoms, and you can maybe see now that this atom right here has 1, 2, 3, 4 nearest neighbor atoms. So here it is color coded again. These are the 4 pink A atoms, and those are the 4 green B atoms. But maybe we can see things better if we draw the atoms smaller. Now I've already figured out the radius to draw, and so these atoms are drawn to scale. They have the appropriate radius. You can see they're barely contacting each other. Okay, so this is the smallest packing unit for a diamond. So here are the atoms drawn a little bit more smaller. We can see things maybe more clearly. Let's draw some more unit cells. So here are 8 unit cells. So there's the first one, and let's fill them up with atoms. Okay. Now, it might be a little bit harder to see, but every single atom has 4 nearest neighbors. And so for instance, this green one is surrounded by 4 pink ones, but pick any of the pink ones in here. Like for instance, this one. This pink one is surrounded by 1, 2, 3, 4 green ones that are closest to it, and there's no other atoms that are closer than those 4. So you can see the green atoms are surrounded by the pink ones, and the pink ones, like here's a pink one right here, it's surrounded by the green ones. Okay? Now we can calculate the distances. Let's go ahead and pick any atom. Like how about this one right here, this green one. Let's go ahead and calculate the distance between it and its nearest neighbors. So you can see it's 1.54. We can do it again right there, and right there. And you can see it's 1.54 angstroms away from all of its 4 nearest neighbors. Okay, and you can find any other atom in the lattice as well. So how about this something way in the middle? So how about this pink one right here? Okay, 1.54. 1.54. Now then another one is this one and that one, and then this one and that one. Okay, now hopefully you can see that there are no atoms closer than those 4 green atoms. So every atom is surrounded by 4 nearest neighbors, and the distance is 1.54. Okay, now we could draw these to scale, but it makes it a little bit harder to see. Maybe you can see, you know, maybe you can actually see a little bit better. You see this pink one, it's touching 4 green ones, and choose any green one. So here's a green one right there, and it's touching 4 pink ones. Okay, so the pink one's surrounded by 4 greens, green surrounded by 4 pinks. Okay. So there you go. Now, let's go ahead and calculate these distances. And the way we're going to do that, here, let me draw all of them again. The way we're going to do that is we're going to consider a right triangle again. So here, let's go back to the paper. So there's diamond. There you go. So diamond is a very strong structure. All carbon atoms are tetrahedrally bonded to 4 other carbon atoms. All right. So here's our paper again, and okay. So the way we're gonna calculate the distance between, say, B1 and A1 is we're gonna realize that this triangle from this corner all the way down to that corner and back over here is a right triangle. This is kind of like the triangle we were doing in the last problem. Okay. Now, if we consider that triangle, I've redrawn it down here. Okay. This is the edge length 3.56. This is 3.56 times square root of 2, and that's the hypotenuse. So here's the short edge, the medium edge, and the long edge. Let me show you this one more time. The short edge, the medium edge, and then the long edge. The edge length, square root of 2 times the edge length, and the hypotenuse. So you got the edge length, square root of 2 times the edge length, and then the hypotenuse. So we can solve for the hypotenuse, okay? It's equal to the square root of this squared plus all of that squared. And then we get it's 6.1661, okay? You would round it to this position. Now, the distance from atom B1 to A1 is actually 1/4 of the hypotenuse. And you can see that, hopefully, by looking at that long hypotenuse right there. You see, the position of B1 is 1/4, 1/4, 1/4, which means that it's actually 1/4 of the way along this hypotenuse. The exact middle of the hypotenuse would have coordinates 1/2, 1/2, 1/2. And then up here, 3/4 along would be 3/4, 3/4, 3/4. But this is only 1/4 along. So the distance from here to here is 1/4 of the length of the hypotenuse. And when we calculate that, that does come out to be 1.54 angstroms. Problem 5 deals with the structure of sodium chloride crystals. It reads, the sodium chloride crystal has a cubic unit of structure with edge length 5.628 angstroms. There are 4 sodium atoms, or ions, in the unit of structure with coordinates, and it gives you the coordinates, and also 4 chlorine atoms with their coordinates. Make a drawing showing the cubic unit of structure and the positions of the atoms. How many nearest neighbors does each atom have? What is the interatomic distance for these neighbors? And what polyhedron is formed by them at the corners? So we'll take a closer look at the polyhedron, but we've answered questions like those other ones before. This arrangement of atoms, called the sodium chloride arrangement, is a common one for salts. Let's take a look at the model for this structure. Drawing some notes here. This also references pages 20 to 26 in the textbook. Talking about sodium chloride, it's a cubic lattice and it gives us the edge length. The 4 sodium cations have their respective positions within the unit cell. And I'll make a note that these are the same positions given in the textbook for the face-centered cubic arrangement, which is the cubic closest packing arrangement. the chlorides have their positions throughout the cell. And I've drawn a representation of the unit cell. Let me show you that a little bit more closely. So the sodium cations are pink and the chloride anions are green. These are positions A1 to A4 and those are B1 to B4. Now, the sodium positions are occupying the same 4 positions as the face-centered cubic arrangement. Okay, and the chlorides, there they are. Now, I'll make a note that cations are usually smaller than anions, usually, unless it's a really big cation. All right, so the chlorides in this case are actually kind of touching with the sodium ions occupying the crevices between the chlorides. Now, as before, it's kind of hard to see everything with just one unit cell, but maybe you could imagine the other atoms in the neighboring unit cells there. If there is a pink atom at this corner, you should reason that there's also going to be one at this corner, this, at all of the corners in all of the surrounding unit cells, because the next unit cell there will be a similar atom, and the unit cell right above there's going to be an atom right there, and there's going to be an atom at each of the corners, and likewise there's also going to be an atom halfway along each of these edge lengths. So right here, right here, right here, and etc. So you can imagine that they're all there. And after you do that, maybe you could then see that this central chlorine atom, which is in the exact middle of the box, that has coordinates 1/2, 1/2, 1/2. Okay? That's in the exact middle of the box. That's going to be surrounded by 6 sodium cations. 1 at the center of this face, 1 at the center of this face, 1 at the face coming out of the paper, and then 1 at the other 3 faces. So this one has 6 surrounding cations, and it's also going to be the case that the cations have 6 surrounding anions. But let's take a better look at this through the computer model. So here is sodium chloride. Okay, this is a 1 by 1 by 1 unit cell. And let's draw the atoms. Okay. Now you can see the chloride ions are much bigger than the sodium cations. In fact, the chlorides are pretty much contacting each other in a face-centered cubic arrangement, with the sodium cations occupying the crevices. Okay, so let's draw some more. You see that face-centered arrangement? So you see there's the face-centered arrangement of the sodiums. There's 1 at each corner and then 1 in the middle of the face. But you know what? If you look at these sodium cations, then look at the chloride anions, it looks like the chloride anions also have that arrangement. Look, there's 4 forming a square, and then 1 right in the middle of the square, just like this. There's 4 forming a square and 1 right in the middle. So in fact, the chlorides also have that same arrangement. It's just the lattice has been shifted over by 1/2. We could have drawn the lattice centered around the chlorides if we wanted to. Okay, but the textbook gave us the lattice with the sodium ions at the corners of the lattice instead. So let's draw these a little bit smaller. Now, do you see how each of the atoms would be surrounded by 6 neighbors? You see this chloride would have 4 neighboring sodium ions, and then 1 behind it, and then 1 in front of it. But let's draw it a little bit smaller so we can see better. Come on, spin you. It's hard to get this thing to spin sometimes. Okay, well, whatever. So if you focus in on any of these central ones right here, like look at this central chloride. It has 1, 2, 3, 4, 5, 6 surrounding sodium cations. And can you imagine what polyhedron would be formed by those surrounding cations? Imagine connecting this one with that one, you know, all of them with lines. Can you visualize what the polyhedron would be? Okay, so think about that. Let's first answer the question that asks how far away those neighbors are. So if you look at this central chloride, well, it's obviously half of an edge length away from this neighbor, and also from that neighbor, and then half of an edge length away from all of the surrounding sodium cations. Okay? And same thing with the sodiums. If you look at this sodium right here, and its 6 chloride neighbors, it's half of an edge length away from them. Okay? So the answer to that is that each sodium is surrounded by 6 chlorides, each at a distance of half of an edge length. And if you calculate half of the edge length, that's 2.814 angstroms. And likewise, each chloride is surrounded by 6 sodiums, each at a distance of 2.814 angstroms. Now, those 6 neighbors form an octahedron around the central particle. So let's take a closer look at that. If you focus in on this chloride right here, you see the surrounding 6 neighbors form an octahedron around it, an 8-sided regular polygon where the sides are equilateral triangles. So this is a regular octahedron with the chloride in the exact middle. And likewise, if you look maybe at that sodium over there, its chlorides also form an octahedron around it. See? With the sodium in the exact middle. Problem 6 deals with cesium chloride crystals. The cesium chloride crystal is cubic with edge length 4.11 angstroms, cesium at the origin, and chloride in the exact middle. How many nearest neighbors does each atom have? At what distance are they? What polyhedron do they define? So this lattice is more simple than the previous cases. There is only 1 cesium per unit cell and also 1 chloride. Now, the cesium positions are at the origin, and if you can visualize this in your mind, think of a large cubic lattice, a bunch of boxes stacked together, and if you have a cesium at the origin of the first box, then that means there's going to be one at all of the corners of all of the boxes. And chloride is going to be in the exact middle of all of those boxes. Now that's actually another lattice called the primitive or simple cubic lattice. So the cesium ions are in a simple cubic arrangement, and also the chlorides are as well, as we'll see. So let's take a look at the model for this. So, of course, same page numbers as before. The cesium chloride structure, this is a cubic arrangement, edge length 4.11. Now, cesium is at the origin, and as I've mentioned, this position, when there's only one of them per unit cell for the cubic arrangement, that's the primitive lattice, okay, or also called the simple cubic. Chloride is in the exact middle. So here is the model. You have the cesium at the origin and the chloride in the middle. Now, if you visualize this in your mind, if you have a cesium right here, then there's also going to be one at each of these corners throughout the lattice, which means that the chloride in the middle would have 4 cesium neighbors up here and then another 4 down there. So the chloride would have 8 neighbors. Each chloride is surrounded by 8 cesiums, and it's pretty easy to calculate the distance between them. And it turns out that each cesium is going to also be surrounded by 8 chlorides at the same distance. So let's maybe take a better bird's eye look at this with the aid of computer models. Let's draw one unit cell again. Okay. Now, cesium is a fairly large cation, and I'm not actually sure which one would be bigger, cesium or chloride, and so I'm just going to draw both of them kind of smaller than they might look like on the atomic scale, okay, not contacting each other. But I would have to do a little bit more research to figure out, is cesium actually bigger than the chloride, or is chloride bigger than the cesium, or are they kind of the same sizes? I really don't know. Because cesium, if you look at the periodic table, it's pretty far down there. Okay, it's several positions below sodium, and so although it's a cation, it's probably pretty big. Okay, so let's draw another one. So there are 8 unit cells right there, and you can probably imagine where the rest of the atoms would go. Let's give this a spin. There we go. Okay. Now, can you see how each of the atoms have 8 neighbors? So look at this chloride right here. You see the 8 surrounding sodium cations. And can you see the polyhedron that those sodium cations define? It's got to be a cube, right? It's in the exact middle of this cube, and those are occupying the positions of the cube. So it's obviously a cube. And likewise for the sodiums, the surrounding 8 chlorides also define a cube. Now again, as in the last case, we could have also drawn the lattice as being centered at the chloride ions. So each corner is at the chloride ions. The lattice would be shifted a little bit. But the way the textbook defined it, the sodiums are actually at the corners and the chlorides in the middle. But it could have been drawn the other way, with the chlorides at the corners and the sodiums in the middle. Okay. So how about the distance between the atoms? Well, we can, consider various triangles, but how about the triangle from, let's say, this cesium, was I saying sodium? This cesium to the middle of this edge length, to that chloride, and then back to the cesium. How about this right triangle right here? So let's put that up there, keep that in your mind. Gonna show you on paper. Okay, you see, here is the right triangle right there. Now, this is a right triangle, and the distance of the short edge right here is going to be 1/2 of the edge length. 1/2 of 4.11 is 2.055 angstroms. Okay? And this is going to be 2.055 times the square root of 2. Okay. So to solve for the hypotenuse, I've redrawn that triangle right there. Okay, you have the cesium and the chloride. So here's the short edge, here's the medium edge, and then the hypotenuse is the long edge. You solve for the hypotenuse, the square root of all that equals 3.56 angstroms. You would round it right there. So there you go. That's the distance between those ions. Now, this was a good set of problems. It took me a while to prepare for these problems since we're using a lot of computer models. Now, if you liked these computer models, then I would encourage you to tinker around with that software, VMD. And in the comments below, I'll go ahead and include the code that is required to generate these crystal lattices that were used in this video. So you have to get used to how the software works, but if you're interested, for students who want to take it maybe a step beyond, then have a go. You probably have to run through some tutorials on how the software works and then tinker around with getting that code to work. Okay? So our next video will finish chapter 2, and we'll take a look at problems. Here they are. Problems 7 through 10, which deal a lot with phases of matter and vapor pressure. So until then, aloha.